Airplanes, rockets, jets, and missiles all travel incredibly fast through the air, with some traveling much faster than the speed of sound. Engineers need to test these high-speed devices before they launch them, and one of the main ways they do that is by using wind tunnels. Wind tunnels allow engineers to predict how air would interact with an object if it was flying at a high speed. In this video, I will go over the history of wind tunnels, how modern wind tunnels work, and show you how I built a working, small-scale model of a wind tunnel. Researchers have been conducting airflow experiments for hundreds of years. In the mid-1700s, Benjamin Robbins used a device called a whirling arm to spin objects through the air and measure the drag force on the object. Although this was a good start, Francis Herbert Wenham wanted something better. In 1871, he invented the first wind tunnel to test different wing shapes. The Wright brothers built a wind tunnel in the early 1900s to test wing shapes and collect data used in the design of the first airplane. Since then, wind tunnels have evolved both in size and speed. Just as wind tunnels have changed over time, so have the shapes of aircraft. The Wright brothers' airplane had a boxy structure with exposed struts and wires. As time passed and more research was done, airplanes started to transform into the shape we know them as today. Unlike the Wright brothers' plane, modern airplanes have smooth surfaces, no exposed struts, and a pointed nose. Hypersonic vehicles take aerodynamic efficiency one step further. They are extremely slender and have very sharp noses and edges. Modern wind tunnels can be used to test objects going at supersonic and hypersonic speeds, allowing engineers to test all kinds of aircraft and spacecraft. But how do wind tunnels even work? Let's say that we want to test an airplane to see how it would behave when flying through the air. We can create a smaller model of the airplane and put it inside of a giant tube. We can suspend it to the base of the tube using a bar that can measure the lift and drag forces that the air will put on the plane. Let's also put a fan at this end of the tube. Now we have a basic wind tunnel. While this design functions as a wind tunnel, most of them look something more like this. The physics behind this design is rather complicated, but I'll give a very brief explanation. This is called the contraction section. The tube becomes more narrow in this section, forcing the air to speed up and the pressure to decrease. Additionally, a honeycomb filter is typically placed here to reduce turbulence. The air created by the fan isn't perfectly smooth. Instead, it looks something like this. This is called turbulence. However, to simulate high speeds, we want to reduce the turbulence as much as we can. This filter helps reduce turbulence and makes airflow more uniform. There are two main types of wind tunnels, open return and closed return. Open return wind tunnels are simpler and cheaper to produce, but they are sensitive to the environment around them. They are also louder and less energy efficient. Although closed wind tunnels are more complex and expensive, they aren't affected by the environment as much and are typically better for repeated testing. Now, I'll show you how I designed and built my own model wind tunnel. I decided to use a handheld air duster to blow air into this clear tube. I 3D printed a contraction section to connect the air duster to the tube. I also glued on this rubber seal to create an airtight connection between the air duster and the part. I also 3D printed a honeycomb filter to reduce turbulence in the tube. I decided to use ribbons to visualize the airflow through the tube, so I attached them to the honeycomb filter. I also built a small rocket out of Legos to put inside the wind tunnel. After putting everything together, this is what the final product looks like. Earlier, I discussed the significance of the contraction section and the honeycomb filter, so let's see how much they actually affect the airspeed of my model wind tunnel. This is an anemometer, a device that measures wind speed. Let's see how fast the air travels with and without the contraction section. By itself, the air duster is blowing air at about 5 meters per second. However, when we add the contraction section, the airspeed increases to about 9 meters per second. Now, let's run the same test with the honeycomb filter. The honeycomb filter increases airspeed to about 10 meters per second. As we can see, both the contraction section and the honeycomb filter increase the airspeed in the wind tunnel. If I was working on a hypersonic vehicle, my model wind tunnel wouldn't be suitable to test it. This is mainly due to the size and speed of my model. Because my wind tunnel is so small, I wouldn't be able to create a very accurate model of my hypersonic vehicle. Larger wind tunnels allow for larger models, which makes it easier to match real flight conditions. Additionally, my wind tunnel only blows air at about 10 meters per second. Because of this, I can only test vehicles traveling at that speed. Hypersonic speeds start at Mach 5, which is roughly 1700 meters per second. If I wanted to test a hypersonic vehicle, I would need a wind tunnel that can reach much higher speeds. Wind tunnels have evolved so much since Wenham's tunnel in 1871, but there is still a lot that can be improved. For example, this support that goes under the vehicle slightly alters the data that is collected in the wind tunnel. In order to collect more accurate data, we would need to remove this support. This could be done by using magnets to suspend the vehicle in the air. This has been done before, most notably with NASA Langley MSVS tunnels, but never at hypersonic speeds. While it would be very complicated and expensive, if this technology could be implemented in hypersonic wind tunnels, engineers would be able to collect more accurate data related to hypersonic flight.